Peter Scholze is one of mathematics' most revolutionary minds of the 21st century, feared by fellow mathematicians for his ability to simplify impossibly complex proofs and his creation of entirely new mathematical frameworks. At age 24, he became one of the youngest full professors in Germany, tasked with advancing arithmetic geometry. When faced with problems in p-adic geometry that had stalled progress for decades, Scholze didn't retreat. He invented perfectoid spaces, a breakthrough that connected previously unrelated areas of mathematics. His first major achievement came with his doctoral thesis on perfectoid spaces in 2012, where he unified arithmetic geometry and representation theory, solving problems that had resisted solution for years. For this, he earned international recognition and multiple prizes. Admired by mathematical giants like Terence Tao for his relentless innovation, Scholze again pushed boundaries with his work on condensed mathematics. His approach penetrated deeper into the foundations of mathematics than anticipated, playing a decisive role in restructuring how mathematicians understand topology and analysis. The result was one of mathematics' most celebrated breakthroughs, with thousands of researchers adopting his methods and entire conferences dedicated to his work. In 2018, Scholze received the Fields Medal at age 30 for transforming arithmetic algebraic geometry. Later, he developed condensed mathematics with Dustin Clausen, where another revolutionary framework simplified complex topological structures. Scholze believed in making abstract mathematics accessible and supported collaborative research. He continued leading groundbreaking work at the Max Planck Institute, earning the Leibniz Prize in 2016 and becoming the youngest full professor at the University of Bonn. His influence reshaped modern mathematics and inspired a generation of researchers worldwide. Akshay Venkatesh became one of mathematics' most versatile problem solvers of his generation, remembered less for working in a single area than for his ability to bridge number theory, ergodic theory, and representation theory with stunning insight. A former child prodigy who competed in the International Mathematical Olympiad at age 12, he already had extraordinary talent before winning the Fields Medal in 2018. Together with collaborators across continents, he delivered groundbreaking results in automorphic forms and ergodic theory, connecting arithmetic properties of numbers to the statistical behavior of dynamical systems. His work on period mappings captured fundamental relationships between algebraic cycles and topology. These results earned Venkatesh recognition as one of the most creative minds in pure mathematics. Though his collaborators provided crucial technical expertise, Venkatesh provided vision and synthesis. He relied on deep analogies between different mathematical structures rather than brute force computation, which allowed him to solve problems that had resisted specialized approaches. After early recognition for his work on quadratic forms, he led further breakthroughs, including applications to homogeneous dynamics and the study of L functions. His ability to find unexpected connections across mathematical fields made him one of the most influential researchers of the 2010s. By 2018, his reputation was so strong that he was awarded the Fields Medal for his profound contributions to analytic number theory. At the Institute for Advanced Study, he continued exploring connections between number theory and topology, pushing the boundaries of mathematical understanding. His work also demonstrated how ergodic theory could illuminate previously mysterious patterns in prime numbers and other arithmetic objects, reshaping how mathematicians approach fundamental questions. Alessio Figalli first gained fame for his work on optimal transport theory, where he proved regularity results that transformed the field. For this, he received numerous awards including the Stampacchia Medal. Soon after, he became one of the youngest professors at ETH Zurich and the main force behind solving long-standing problems in partial differential equations. He tackled the Monge-Ampère equation, where previous approaches had failed, developing new techniques that established regularity in previously intractable cases. He also directed groundbreaking research on the isoperimetric problem and phase transitions, where his methods resolved conjectures that had stood for decades, securing his position as a leader in mathematical analysis. By 2017, Figalli was driving progress on multiple fronts, proving the stability of geometric inequalities and characterizing optimal shapes in calculus of variations. He pushed for rigorous mathematical foundations in problems arising from physics and engineering, demonstrating applications from soap bubbles to crystallization. In 2018, he received the Fields Medal for his contributions to optimal transport and partial differential equations. He turned his attention to free boundary problems, developing the theory that explained how ice melts and how interfaces evolve, work that earned him further recognition. Figalli was known for his clarity of exposition and his ability to extract concrete results from abstract theory. His techniques became standard tools across analysis, influencing researchers in geometry, probability, and mathematical physics. He later solved problems about the shape of ice crystals and contributed to understanding singularities in geometric flows, cementing his legacy as one of the most productive analysts of his era. Caucher Birkar, born in Kurdish Iran, became one of algebraic geometry's most determined researchers. He fought through political instability and arrived in the UK as a refugee before rising to prominence in the classification of algebraic varieties. His approach relied on persistence, deep technical mastery, and the willingness to tackle problems others considered impossibly difficult. Instead of avoiding singular spaces, Birkar developed methods to study them directly, using minimal model theory and boundedness results to chart the landscape of higher-dimensional geometry. Early in his career, he earned recognition for progress on the finite generation conjecture, proving cases that advanced the minimal model program. By 2010, his research was achieving decisive results on Fano varieties, where he established boundedness theorems that had eluded mathematicians for years. Working with collaborators including Christopher Haken and James McKernan, Birkar helped complete the minimal model program in higher dimensions, a monumental achievement that restructured algebraic geometry. His most celebrated work involved proving the Borisov-Alexeyev-Borisov conjecture for Fano varieties, demonstrating that these fundamental geometric objects come in finitely many families in each dimension. Birkar's relentless pursuit led to over 60 published papers addressing some of the hardest questions in birational geometry. At the 2018 International Congress of Mathematicians, he received the Fields Medal for his contributions to the minimal model program. Tragically, the medal was stolen minutes after the awards ceremony, though it was later replaced. Returning to Cambridge, he continued as a leading figure in algebraic geometry, mentoring students and driving progress on classification problems. His journey from refugee to Fields medalist became an inspiration, demonstrating mathematics' power to transcend borders and adversity. Jun He entered mathematics through an unconventional path, studying poetry and physics before discovering his passion for the subject in his mid-20s. He became one of the most original minds in combinatorics, solving problems that had resisted proof for decades using techniques from algebraic geometry. His style relied on seeing hidden geometric structure in discrete objects, transforming combinatorial questions into problems about algebraic varieties where powerful tools could be applied. By 2018, working with collaborators Eric Katz and Karim Adipresido, he had proven broader cases of the Rota conjecture for all matroids, not just those arising from geometry. His methods revolutionized combinatorics by importing sophisticated tools from Hodge theory and tropical geometry, areas previously considered too abstract for discrete mathematics. In 2022, He received the Fields Medal for bringing the methods of Hodge theory to combinatorics, proving the Dowling-Wilson conjecture and the Heron-Rota-Welsh conjecture. He continued work at Princeton, developing the foundations of combinatorial Hodge theory and inspiring new generations to explore connections between algebra, geometry, and discrete structures. He's success demonstrated that mathematical talent can emerge at any stage and that the deepest insights often come from seeing connections others miss. His work opened entirely new research directions that dozens of mathematicians now pursue. Hugo Duminil-Copin is one of statistical mechanics' most precise problem solvers. He became known for his rigorous proofs of phase transitions in lattice models, bringing mathematical certainty to problems physicists had studied experimentally for decades. His approach combined probability theory, complex analysis, and combinatorics to prove that certain physical systems undergo sharp transitions between ordered and disordered states. Early in his career, Duminil-Copin earned recognition for work on the self-avoiding walk, proving conjectures about how random paths avoid intersecting themselves. In 2022, he received the Fields Medal for solving long-standing problems in percolation and statistical physics. At the Institut des Hautes Études Scientifiques, he continued work on critical phenomena, proving universality results that explained why different physical systems exhibit identical behavior near phase transitions. His research bridged pure mathematics and theoretical physics, demonstrating how rigorous analysis could confirm or correct physical intuition. Duminil-Copin's contributions gave mathematicians powerful new tools for understanding randomness, connectivity, and the emergence of large-scale structure from local interactions. James Maynard emerged as one of analytic number theory's sharpest minds, solving problems about prime numbers that had stood for generations. He became famous for his work on gaps between primes, improving results that had just been established by Yitang Zhang and the Polymath project. His methods relied on sieve theory and careful optimization of technical parameters, pushing known results to their natural limits. Maynard's doctoral work already contained breakthroughs, including new bounds on the smallest gaps between consecutive primes. He proved that this earned him the Sastra Ramanujan Prize and immediate international recognition. By 2019, he had proven that any admissible set of intervals contains infinitely many primes, a result that applied powerful harmonic analysis techniques to classical number theory questions. His work extended beyond prime gaps to the distribution of primes in arithmetic progressions, where he established new lower bounds on the density of primes satisfying multiple congruence conditions simultaneously. Maynard also made progress on the Duffin-Schaeffer conjecture, collaborating with Dimitris Koukalopoulos to prove this fundamental result in metric number theory. In 2022, he received the Fields Medal for contributions to analytic number theory, particularly for understanding the structure of prime numbers. At Oxford, he continued investigating Diophantine approximation and problems about the decimal expansions of primes. Maryna Viazovska, one of mathematics' most elegant problem solvers, solved the sphere packing problem in dimension 8, one of geometry's oldest questions. For centuries, mathematicians had wondered how to arrange spheres to occupy the maximum amount of space. The answer in 3 dimensions, the pattern seen in stacked oranges, was only proved in 1998 by Thomas Hales using exhaustive computer verification. Higher dimensions seemed impossibly difficult. The mathematical community immediately recognized the importance of her work, awarding her the Salem Prize, the Clay Research Award, and other honors. In 2022, Viazovska received the Fields Medal, becoming only the second woman to win the award. At the École Polytechnique Fédérale de Lausanne, she continued exploring modular forms and their applications to optimization problems in high dimensions.